Hey, hello my friend, and welcome in this new recording. This is Nervland Devlog session number 26, I believe. And as you can see, we have a new format now because I could finally connect my camera to my computer, so very happy with that. Yeah, anyway, let's just dive into the content. We are going to talk about physically based rendering today. And yeah, this is the example that I've been constructing with my engine. And in this small scene, I can actually demonstrate a bit the implementation of PBR rendering. I mean, the initial version of it, it's pretty limited because we're not including any kind of environment mapping yet, or actually even textures on the object themselves. So it's really naked PBR for the moment. But that's the first point. What we have here are a couple of spheres, and we have four different lights moving around. And in this small tool, small experiment rather, we have this control panel, which I can use to control the settings that we have applied on the two spheres. For instance, I can control the roughness here. So you can see that if I reduce that, I'm making the material less rough. And you can do the opposite. You can also control the metallic aspect of the material to make it more metallic or not. And we can in fact apply different configuration for your material, different default configuration. So if you specify gold, for instance, it's going to change the color of the material and apply a default roughness and a default metallic setting like this to here. And you can change that, and then you can keep tweaking the roughness and metallic settings, but not yet the color. I didn't include the color on the GUI, but it's just a matter of adding another GUI element, of course. So what else can we do? We have this small debug feature, which is going to overwrite the roughness on depending on the current location of your fragment. So just for debugging, of course, and you can just pause the animation of the light position or resume this animation. So this is it. But before we go into more details on the actual PBR rendering, I think I should mention a few of the preliminary steps that I took. And the first one we need to talk about is this, the fact that we can now move around with the keyboard action to go forward, backward, left and right, and even up and down actually. So I have implemented the free fly camera controller, and this is what I'm using actually by default now. So let's jump into the code to try to find where we do all this. So this is the PBR basic simple code. And concerning the free fly camera, what should I say about that? The implementation is when you create a camera, basically. So that's going to be, let me find out. So when you set up the application, create cameras, it's going to create a WGPU camera. And can I go there, please? Yes. The constructor that you have for this one may take some construction information, but I think I'm not even using that yet. But in the construction, yes, at some point we need to create a camera controller, and that's where I'm going to create my FreeFly camera controller now, replacing the previous target camera controller. Of course, this is not very good. I should eventually provide an additional configuration element in the create information structure, so that I could decide which kind of controller I want to have in case I still want to stick with the target camera controller. But yeah, for now, we don't really have the choice. It's this one. And okay, let's not spend too much time on this one. if you need more details on how to implement a free fly camera, that's another kind of recording I could do eventually, but for now, it's not really the focus of this session. Another thing I changed, which is very important, but it's technically not very well. It's a technical detail. I've changed the way I construct my matrices because I have a dedicated class. And before I was in fact using a row major matrix implementation, but WebGPU is in fact column major. I mean, it's using column major matrices, which mean that before, every time I was to send a matrix on the GPU side, I had to first transpose my matrix to switch between row major to column major data storage. So yes, I've changed that because I thought it was a bit too much of a pain, and if I eventually start using more matrices, having to transpose the data every time you want to send that on the GPU, yeah, that's probably not good. So the change I made is in fact very handy, because before I was in fact accessing the matrix data directly, but what I did was to introduce simply a macro like this one, and this is the one I'm using now everywhere in this implementation. So whenever you need to access one of the matrix element, you call this matrix. RC is for row column, and you provide the row number and the column number. But then this doesn't depend actually on how you're doing the storage itself. So what we just need to do is to define how we access the data here, and you're going to use the column first, so column major, and the row as the second element here. So yeah, with that, I could get rid of all the transposition and everything was still working just fine. So great. Another small change I did was to add support for the quit event in my window when I have a GUI frame inside it, because otherwise, if you give the focus to your panel here, it's going to prevent you from pressing. From exiting the window. If you close it here, it was preventing me, but now it's not anymore. It's working just fine. And again, that's a small detail. We don't need to talk too much about that. What else? Yeah, I've also introduced the support to resize the window. So resizing the swap chain. So now when we resize the window like that, it's going to accept the change of the size. And there's actually quite a lot of stuff going on in the background with this, because when you resize the swap chain and you are actually using the swap chain for rendering some render passes, you also need to take this into account when you're building your render passes. When you're encoding the render passes. So we already had that in place. In fact, if I have a look at the render pass implementation, maybe rather here. When I build a render pass, I could use this add swap chain color attachment, and this one would actually provide a function that would dynamically retrieve the swap chain and get a texture view corresponding to this swap chain. And this is what would be used as a color attachment when you're preparing your render pass, every time you need to encode the render pass. And yeah, it means that whenever the size of the actual swap chain corresponding to this index is changed, you would get this reflected here in your view. But the thing that was missing was actually about the same thing for the depth attachment, because this one was fixed for me so far. So what we have now is this additional function, add swaption def attachment. So again, this def attachment will depend on the current swaption configuration. And so if the size of the swap chain is changed, you get this this callback executed. So you get the swap chain size, and if it doesn't match the current def texture, then you actually rebuild another def texture. Okay, what else should we mention concerning the preliminary stuff? I think this is it. So now let's have a look at the actual PBR experiment itself. So for this one, what I use as a starting point was, I have that here. So I think I mentioned that already a few times. This web GPU native examples repository on GitHub. So on this one, you have this PBR basic example. But again, this is in C, so it's pretty large. Nothing you would like to use. For real implementation, I guess. And in this one, you're going to define a few different materials like this. And it's also supporting changing the actual model that you would use for the rendering, but this is not implemented yet on my side. For now, I'm really just rendering with a sphere, but I could make this differently at some point. It's not the priority for me. And so we took basically the same list of materials here. And what else? We need some kind of structure that we can send to the GPU, of course. And what we do is, we discuss about this construction function later, but let's first have a look at the setup of the application. So what we do is we create the camera, and the frame provider is just going to provide me the current time of the simulation, basically, which I was using at some point to do some testing, but it's not really relevant here. Then you prepare the skybox. That's a big deal. And then we do the rendering here of a couple of spheres. So there's the first one, which is located at the center of the scene because of the model matrix that we're providing here. So Matt is just going to scale this sphere up a little bit. And then there's a second one, which is using exactly the same settings, except that the model matrix for this one is translated a little bit on the right, but still using a scale factor of 2. And for those two, we're using this PBR basic shader, so we can have a look at this one. For the vertex shader, there is really no big deal going on. In fact, you just start with a standard input. Let me just... Okay, and from this input, you get the position and the normal of your current vertex. The position, you use that to transform it into the world position for your vertex. And you do the same thing for the normal, because you need the world normal of the current vertex. I was, as I said, doing some experiments on trying to modify a bit dynamically the shape of the sphere. So I was moving the vertices along the normal with cosinus. But yeah, not really important, I guess. And what you need to do then is to send those two onto the fragment shader. And in fact, so again, this is coming from the implementation that we have in C. So you can have a look at the PBR vertex shader here. So GLSL implementation, it's going to compute the world position of your input position. Except that, yeah, the objects could be moved, and you could it would actually render multiple objects in this case. So we're not doing that. We're just rendering a single object for the moment. And it's also computing the word normal using the vertex input normal. And those two are sent to the fragment shader because these are varying locations. Okay, and then for the fragment shader, this is the one that I use as a template. And the main function, as you can see here, is going to use this input position and input normal and do some computation. So this is what we have replicated on our side here in the main fs function. So you start with the normal, you compute the v vector. Oh, another thing I did not mention is you also need the camera position, the camera world position. In fact, you can get that from your the inverse of your view matrix, or well, the view matrix, depending on what you actually call view matrix and what you call inverse view matrix. But in my case, it's the inverse view matrix. And so I'm also now providing this inverse view matrix directly into the web GPU camera. So there's a structure, yeah, the UData structure that you send. This is going to send the view matrix itself. Yeah, the naming convention here is not good. Anyway, so you can access this inverse view matrix in the shader, and I'm doing that to retrieve the camera position. Camera, we have the inverse view matrix, and we have this get camera position, which is just going to retrieve the last column of your view matrix, which is a translation of your camera in the world coordinates. All right, that's a small detail again. So yeah, you do some computation here. Basically, for every single light that you have described, you're going to compute this BRDF function. And this BRDF function is defined just before. And this one is going to call other sub-functions like this distribution, GGX, blah, 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 and flick, blah. Okay. So you have all those functions defined just before, and they're again coming from the implementation that was available here in the C version of the experiment. Okay, what should I mention else? What is interesting here maybe is the new stuff that I have introduced concerning how we can manipulate structure on the C++ side and map that to buffers on the GPU side. Because what we had in place so far was buffer providers. Like for instance, the camera is a buffer provider. The frame context provider is a buffer provider also. And with those buffer providers, what we can do is we have this class camera, for instance, which is going to define a structure on the CPU side, and it's going to update the structure on every frame and synchronize the buffer, the GPU buffer, the corresponding GPU buffer on every frame. Well, you could optimize that and only synchronize if there was any change, but it's still going to execute some kind of logic on every frame. So we have update buffer function in those buffer providers. So I wanted to have some kind of mechanism that would allow me to keep the synchronization between a CPU structure and a GPU buffer, but make it well, manually, so that the user would be responsible to, I mean, the developer would be responsible for requesting the synchronization only when this is needed. And for that, I have implemented what I call the dynamic buffer. And we're using that, for instance, for the material data that we want to send to the shader, or the scene data, which is going to describe what are the light position, the number of lights, and yeah, a small flag actually, which is going to tell me if I want to enable or disable the roughness strip debug display. So we have those uniform buffer now, and uniform buffer is actually some kind of dynamic buffer, but with the uniform buffer usage. And we also have another one, which is a storage buffer. I'm not using that yet, but eventually I'm probably going to use it. And this one is going to have the usage of storage instead. But both of them are simply dynamic buffers. And this dynamic buffer, you would create that with a given structure as input template parameter, and it would keep such a structure inside this class and also create the corresponding buffer. And then you can just decide to access the structure, modify whatever you want on it, and when you think you're ready, you would call update to send the data on the buffer. And this is what I'm using, for instance, for, let me check the time, okay, for the GUI manipulation. So we have this construct GUI function where we build the IM GUI interface, and in there we are going to retrieve the structure inside those dynamic buffers, and you can then start changing some of the values that you have on those structures. So let's see, for instance, this matte structure, we're using that here when we are defining the slider for the roughness. Then I'm using the dynamic buffer again, but I could simply use matte. Exactly the same in here. And so you would optionally update the roughness value with this call. And if you notice that there's a change, the return will be true. So you can then figure out that, okay, you actually updated the material data. So you need to send the updated data on the GPU side. And that's where you would call update on your dynamic buffer. So we do that, for instance, to control the material settings, and also for the scene settings, because when you're not pausing the animation, you want to continuously update the position of some of the lights, actually. So only two of the 4 lights. And when you do that, you also need to send the updated data on the GPU side. So you would call update on the scene dynamic buffer. And yeah, so the initial content for the scene data is set once here before starting anything, and then it's going to get updated continuously, except if you check the pause animation checkbox on the GUI. So that's a nice thing. Also, while I was at it, that would have been another issue next when it comes to calling this render node. Well, actually, that's a template function taking an arbitrary number of arguments, and all the additional arguments that you are passing at the end here are binding entries. So you need some kind of mechanism to convert the input that you're providing into a binding entry. So for instance, if you're just specifying a string like that, it would try to find a buffer provider with this name and link the underlying buffer as a uniform buffer. So introducing those new dynamic buffers, I would need then to connect those dynamic buffers to actual binding entries here. And one way to do it would have been to create a new function that would be something like make UBO and taking a matU, a dynamic buffer, as argument. But yeah, I thought it would actually make it a bit more easy to have those functions directly integrated onto the dynamic buffer itself. And this is actually a concept that I could extend a bit later. And maybe if I have other classes like that, I could again provide functions like as UBO, as storage, as read-only storage, and this function would create the binding entry for me. So what we have here, for instance, this one is going to call simply as UBO with fragment set to true, and this as UBO is going to create this famous binding entry for me. And it's going to simply use the buffer that we have in this dynamic buffer as the buffer for the entry itself. So I think this is going to be pretty handy and will certainly help to make the writing of the code a bit more understandable and less crowded, maybe. We'll see. Or maybe we have to evolve this further. And yeah, what else should I mention? Let me see. Oh, yes. One last thing I think I should note here is on the integration of the IMGUI interface rendering process. In the previous example, which was about integrating IMGUI, we were building and initializing IMGUI directly here in the setup app function. So you have a lot of code related to this initialization process, actually starting from here to the end of the function, I believe. Because here you're setting up a dedicated render path to render the GUI. Then you have additional event handlers for the main window manager itself. What else? There was also here some part in the render frame to invalidate your data when there's a resize of your swap chain. Then you do the actual rendering of the GUI, so this line, then this part, then yeah, everything concerning this is for IMGUI. And at the end, you could also do this part, even if it's not really working yet. Eventually, this might work, and you will need to process the additional windows when you're done with your main window. So, and even here, you would have to destroy IMGUI when you're done running your application. This process was changed completely, and now in the PBR basic example, all we really have is just use IMGUI true, and then you have a dedicated function to build the GUI, construct GUI. So what's happening under the hood is we have introduced a GUI manager component into the web GPU engine. And this component is completely integrated into the engine, and it's going to, well, render itself on its own without you having to worry about it. It's actually hidden partially, for instance, in this function, pre-render. If we go and have a look at this one, you will see that it's going to get access to your GUI manager first, request to render frame, and after that, it's going to do the update UBO providers. So if you go there, you would see that in case IMGUI is not used and you don't do anything, but otherwise you start a new frame. If you have any kind of builder which can be attached dynamically, then you would call those builders at this point, and those builders are what we use to actually build the GUI themselves. And the construct GUI function, for instance, the one I mentioned just before, this one is registered as a dedicated builder, so it's going to be called every time a new frame is requested. So you do the building here, then you do the rendering, the actual rendering, And we even have a dedicated render pass. So here, creating a dedicated render pass, which is not even registered into the engine itself, because the engine, in case you didn't really notice that before, whenever you create a new render pass here, those render passes are registered 30 minutes, okay, are registered in the engine, and then you can request the execution of those render passes by ID. So it means that if I were to register the render pass for the GUI rendering in the engine, then you would have to take that into account when it comes to selecting the proper ID here for the render passes that you actually want to render on a given pass, on a given frame. So yeah, not registered at all, and it's rather going to submit the rendering for the GUI render pass. I think it's this in the submit. Yes, in the submit. If we have with GUI enabled, which is a default value, by the way, then you are going to render the GUI on top of the previously executed render passes, and render GUI is going to render the final render pass from the GUI manager itself. So you see, it's pretty integrated, and you don't have any trace of IAM-GUI processing apart from actually building your GUI, which is the only part which is meaningful, I guess, whenever you create a new simple file like this one. So yeah, I think this is it. Again, pretty long recording, so let's just stop here, I think. And as I said, this was only the first step in PBR processing, because the next step is going to be to add support for the environment maps, and yeah, and after that there will be another step again to add support for actual textures, using actual textures to prepare your material and send those textures and integrate them into the PBR rendering. Pretty tricky, actually. Anyway, thanks for watching. Again, if you have any question, just let me know in the comment. If you want to see something special also, and you would have an idea for a new recording, let me know. And meanwhile, happy coding on your side, and have a nice day. Bye bye.